So this whole section on 3.5 is dealing with the derivatives of the trig functions, the 6 trig functions. We're going to start with looking at the derivative of a sine and cosine. And we're going to start by looking at this kind of theoretically, and then we'll kind of, today I want to kind of develop the idea of the derivative of the sine and cosine mostly, okay? So one of the things I want to do on this is look at a basic graph here of these two things. We're going to look at these limits, and then we're going to look at this kind of numerically like this. All right, so let's get the calculator out. Let's just look at this with the calculator. Okay, that'll be the easiest way, I think, to help you see this. So when you're doing a graph of a trig function on your calculator, make sure that you're in radian mode. So I'm going to press my mode button and make sure that I'm working with radians here. Okay, and then we're just going to put in, let's start by putting in the graph of sine x over x. So you want to put this in like this, just do the sine x, be sure you close parentheses, then divide by x like that. So that's how you want to get that put in. And then let's see, a window. Now we're only interested in this graph around 0. So let's make a window kind of like this. Let's go like negative 1 to 1. Just kind of keep it simple here. And let's go for a y window. Let's do something kind of like negative 1 to 1 also. Let's start that way and just kind of see what kind of graph we have here, okay? So in looking at this one, if you get your window set up like that, let's see what we got here. Okay, now this is a little bit different than a sine wave like that. So what we're going to have is a graph that looks kind of like this. And then we're just going to reason out what the limit is. Just kind of look over that. Come on, move over there the way you're supposed to. All right, so everybody got that okay on their calculator? Okay, all right. Well, if you're looking at your left-hand limit and your right-hand limit on this as x goes to 0, that's what we're interested in, is that's negative 1, that's 1. Is the way we set up the window. I mean, it's pretty easy to see what this is. If you're going from the right, what does it appear the limit's going to? It appears that it's going to 1, right? Okay. If you're doing the left-hand limit on this, does that look like it's going to 1 also? Yeah, so what we would conclude just visually is you could conclude that that's what that limit would be, was equal to 1. Now what's happening on this is your graph actually has a discontinuity in it. There's a bubble right there because this function's undefined at 0, right? Can't have 0 in the denominator, so that's how that would go. All right? Okay? So that would be what that graph looks like. I just want to establish these things kind of on the calculator. All right? Let's do the second one, and let's type this one in. I graph from negative pi to pi. You could also do negative 1 to 1, so I'm going to erase this. Then I'm going to put in, and you got to be careful how you put this in. You got to have the cosine of x like this, and then minus 1. Close off the parentheses, and then divide by x. So you want to get that in your calculator like that. This time I'm going to change my limit. I don't think it's necessary, but I'm going to go ahead and do that. I'm going to have you make the x minimum just go negative pi. Like that, and that just changes it to decimals, and then do the max to pi, like just to pi. Okay, and then we can scale. Let's scale by pi over 2 this time, and I think we can probably just leave the y values like it is, and then you can type a graph in and see kind of how that looks for you there. But be sure you get everything put in the correct way. So I'm going to go ahead and graph this. Now we're just going to look at the limit visually and see if we just get the idea of what that limit is. The reason we're doing these limits is you have to understand these limits to understand the derivative of sine and cosine. So that's what your graph should basically look like, is like that. Yeah, now this one's kind of the same idea. If you do this one's also got a discontinuity at 0. So there's really a bubble there, like that. All right, now what does it look like the left and right limit is on this as you go to 0? Looks pretty much like 0, doesn't it? If you're going from the right, that looks like that's going to 0. If you're going from the left, that also looks like that 0. Okay, so all I want you to do is just see these things visually to begin with in this section. Okay, so the conclusion we're seeing on this is these turn out to be two real important limits. We have to understand those two limits before we can even develop what the derivative of a sine and cosine is. Okay, like that. Okay, so let's move to this page. Now I'm going to talk you through this this thing just a little bit here, because what I just showed you is a technological, kind of an intuitive approach. This is an analytic approach, okay? And you want to kind of start getting to the point where you can go through some of these, understanding these analytical techniques on this. Okay, so watch this carefully. This is going to be something I want to just kind of see if you follow. I just went ahead and typed out the steps on this. What I'm going to do is I'm going to prove analytically that the limit of sine x over x is 1. I'm going to show you how you prove that, basically. Okay? Mathematicians, if you look at a graphing calculator, that doesn't prove anything, by the way. It just gives you an idea. Okay, it's not a proof. Okay? Calculators sometimes can be deceiving. So what I want to show you on this a little bit is this thing. We're going to look actually at 3 regions. Okay, we're going to just kind of look at this and just kind of think in your mind. We're going to look at this triangle ODA. That's a triangle right there, ODA, like that. Then we got a arc. We're going to look at an arc of a circle, okay, like that, where that's ODA, but that is now an arc. So whereas this is a triangle, this is an arc. And then we got this big triangle, like this, which has a base of OC, and then it has a height of CB like this. So I'm just going to go through a few things and mostly kind of talk through this and see if you guys follow this.
Wouldn't your second triangle be OCA?
What's that?
Wouldn't your second triangle be OCA?
Oh, the big one is, okay,
Second.
This one is an arc.
Right, so it's OC.
So it goes like OC, oh no, that's O, yeah, thank you, it's an arc, it's not a triangle, that's a good point. Okay, so what I want to just do is sort of talk you through this proof here a little bit, because it does have the squeezing theorem in it, and that's always kind of a good thing to show students a little bit here. So yeah, that's OCA, okay? So here's the idea. First, here's the idea. This is what a mathematician thinks of. Okay, would you agree that that area is less than the area of the arc? That's pretty obvious, right? Yeah. And then that arc is less than the big triangle. So what you're doing is you're looking at this area, and that area. You kind of got an inequality that's going to go on there, right, like this, okay? Now I'm just going to talk through this and just kind of see if this connects with you here and everything. This is a unit circle. So the other thing that we have on here is, since we're doing this with a unit circle, is we would know that this piece right here is equal to 1, okay? And that would also tell us that this piece right here is also equal to 1. Okay, we know that. Now this, don't worry about that 0.74. That really is just x. We're just going to use x as 1 radian. Okay, that's going to represent radian measure is what it's going to represent. Okay, so if we were going through and doing the area, this is kind of what we would have. So I want to kind of look at these things right here and see if this makes sense from your trig background. Okay, let's just focus on that for a minute here. Okay, so if you're looking at the sine of x, okay, x is your angle right there. The sine we know is what? Opposite over hypotenuse, right? So that is AD over OA. That's what that is. Now what is OA?
That's 1.
It's 1, right? Okay, this is unit circle. So the sine is opposite over hypotenuse. However, OA is 1. So what you get on this is you get this. You get this result right here. So since that's equal to 1, then we would conclude that the sine x is just equal to AD. Okay? Now look at the cosine. Okay, if you look at the cosine of that angle, remember that x is a radian measure of an angle. The cosine, what is it? Adjacent over hypotenuse, right? So in this triangle, we would have OD over OA, right? Everybody see that? Adjacent over hypotenuse like that. And what's OA again?
1.
1. So you have OD over that. OD, overdose. Okay. So you have that over 1, so that gives you OD. Okay, does that make sense? Okay, right? So what you would get is that result, and that's just because you have a unit circle. And again, you got to know your ideas here. So you're going to get cosine of x equals OD. Okay, now look at tangent. Okay, what is tangent? Tangent is opposite. Now we're going to look at the big triangle on this. So look at the big triangle. If you look at x, opposite is BC, and then adjacent is OC, like that. Okay, so what we end up getting is that result like this. And again, in this particular thing, what's OC? It's 1. Okay, so what you get is the other conclusion is you get tangent of x is just equal to BC. Okay, you guys follow that? Okay. Now, here's a couple of other trig things that we're going to do, and I'll kind of see if you understand this or not. Okay. So what we have here is we're going to find an area of a triangle, OAD. Remember what we're trying to do is compare these 3 areas and set up an inequality, because we're going to use the squeezing theorem on this. So the idea with this is what's the area of a formula? What's the formula for area of a triangle? 1/2 base times height, right? So I'm doing 1/2 the base, OD, times the height, AD, like that. Okay, that's what I'm doing. 1/2 base times height. But OD we had was the cosine. AD we had was the sine. So the area of that small triangle is 1/2 cosine x sine x. Does that make sense? Okay. Now, go back to trig. Do you guys remember what the area of a sector formula is? No. 1/2 alpha r squared. Okay. Now, what you're doing on the area of a triangle is 1/2 base times height. But this is 1/2 r squared alpha. Okay. So here's what happens on this one. Okay, this goes like this. Okay, you got the 1/2. R, this is a unit circle, right? That's why there's a 1 there. What's alpha? Alpha is x. That's the angle. So that is 1/2 r squared alpha. So we have that. Now, if you simplify that, you just have, the 1, you have 1/2 x, or you have x over 2. So that area right there is x over 2. Okay, that's a different formula. Now, the area of the big triangle is real simple. Okay, again, it's 1/2 base times height. So the base is OC, the height is BC, and then we said on this one, we said the tangent was equal to BC. See, OC is 1. That's 1. You can tell by your diagram. And then BC is equal to tangent. So that becomes 1/2 tangent x. So these are your areas right here. This, this, and this. You guys follow that fairly well? Okay. Now, what we would do from here is we put this together and we do this. We're going to kind of follow an inequality. So that goes there. Here's the sector. Here's the big triangle. You're just comparing those 3 areas like that. Now, what I'm going to do with this, I'm not going to go through all the details of this, but if you run through this and do some basic algebra on this, what I want to show you is what you'd have left here at the end. You're kind of doing some basic algebra. And what you're kind of doing from here is you would have 1/2 cosine x sine x, like this, less than x over 2, less than 1/2, and then I'm going to change the tangent to sine x over cosine x, like that. Okay, and what I've done is a couple of simple things on here. What I did is I went through and multiplied everything by 2. So if I multiply everything by 2, that'll get rid of all the 2's. So then I would have cosine x, sine x, less than x, and then less than sine x over cosine x. Okay, and then what I basically did from there, I think, is I ended up going through and doing reciprocals of both sides. And ultimately what you get through on this is you end up, when you do some rearrangement on this, is you get this. Now what happens on this particular thing right here, this is what I mainly want to show you, is if you do the limit of the cosine x as x goes to 0, and then if you do the limit of the outside part, the limit x goes to 0 of 1 over cosine, what I'm showing you is the squeezing theorem here, okay? So if you looked at a unit circle, what is the value of the cosine at 0? 1. So this thing becomes 1, that thing becomes 1, and therefore that's 1. You guys remember the squeezing theorem a little bit. Okay, so what I really showed is this. I ended up going through, and once we got this inequality built, okay, that goes to 1, that goes to 1, therefore that goes to 1 by the squeezing theorem. Okay, so what I'm trying to do is the squeezing theorem shows up a lot in theory. Okay, and we have to have that as a tool to help us figure out that limit. Okay, I don't expect you to do that proof. I just want to see if you follow it fairly well. What do you think? Okay, because I mean, the higher up you get in your studies, the more you have to start looking at stuff like that and thinking through that stuff. So it's good to begin to look at that at this level. Okay, so here's what we're going to do. Well, I'm going to do a little bit of work with limits on this. I do want you to be able to do some basic limits on this section. So we're going to go ahead and look at this, figuring out this limit with a graph and analytically. Okay, so the first thing I want to do with this is have you get your calculator out, and we're going to look at this analytically, which is never a problem for anybody usually. So let's put in sine of 4x divide by x. Okay, you can just keep your window from negative pi to pi. I want to get that put in. And that's my window, and then just do a graph. I'll put my window over here so you can see that. Okay, then I'm just going to have you sketch this graph real. Oh, I need to change. No, I think I'm okay. I do need to change the window. I forgot. So I need you to do one thing. That 4 has something to do with this problem. Okay, so change your window to, for your y's, make your y's go from like negative 4 to 4. Like that, then graph it. Okay, then we're going to look at the limit just visually and see what that is as x approaches 0. And then we're going to look at this same thing analytically. Okay, if you look at the graphing calculator, why did it do that? If you look at the graphing calculator, what does it look like that limit is going to be to you?
4.
What? 4. Yeah, it looks like 4. That 4 has something to do with the problem, obviously. So again, your left-hand limit looks like it's going to 4. Your right-hand limit looks like it's going to 4. So it's going to go to 4. And you do have a discontinuity. You have a bubble there. The calculator doesn't show that. So that's pretty easy. You can tell visually what the limit is. Now what we're going to do is we're going to look at this analytically. So the first thing that you've got to learn how to do is you need to write down this limit. This is the one I just proved with the squeezing theorem. So the limit as x goes to 0 of sine x over x, if you go through and go to the previous page, I'll come right back here, we learned that the limit of sine x over x is 1. Okay, that's what we did with the squeezing theorem just a few minutes ago. So what we're going to do is we're going to use that fact to figure this out analytically. Okay, so here's what you do in this particular problem. It requires a trick, so watch carefully. It's not that hard, but it requires a little trick. Okay, what we're going to do is we're going to start with write down the limit that we're doing. You want to go ahead and get that written down. Okay. Now, what I'm doing is I'm going to teach you how to figure this out analytically. Later in the semester, we learn something called L'Hopital's rule, and you won't ever do it this way anymore. But it's just kind of gets you the idea. So what I'm going to do is I'm going to show you the trick. We're going to multiply the top and the bottom by 4, and there's a reason why I'm doing that. Okay, and that's a valid thing you can do. The reason I'm doing that is because that gives you a 4x there, and it gives you a 4x there. Okay. So what we can do here is we're going to do a substitution. So we're going to just pick any letter you want. Let's say V. Let's let V be 4x. Okay, so what I'm going to have you do is replace that 4x with v. And now let's write down what we have. So that means we would now have the limit as x goes to 0 of sine of v all over v. Oh, I'm missing something. I'm missing my 4. You still have that leftover 4, so you got to be kind of careful about that. See, that leftover 4 is still there, so you'd have 4 times sine of v all over v like that. Okay? Does everybody follow that okay? All right? Okay. Now, what did we learn you can do with a constant when you're doing limits? You can pull it out. Okay? Now we're talking about limits, not talking about derivatives. You can pull it out. So what you would have is 4 times the limit as x goes to 0 of sine v over v. Okay? Now, let's see how observant you are. Can you tell me what the limit of sine v over v is? It's 1. Okay? That is the same thing. I just changed the variable. So what you would end up having is you would have 4 times 1, so you get 4. Now that's analytically how you show that. And you got to be flexible. You got to know how to do technology, and you got to know how to do things analytically. Okay? If we didn't have the analytical part of math down, we'd never develop all these ideas. Okay? Okay, so let's do one more like this. You'll begin to catch on to a little trick on these things, by the way. Okay? But it's just kind of a methodology that kind of helps students a little bit. This time I'm going to do example 2. I'm going to do it analytically, then we'll come back to a graph. Let's go ahead and go to the next page, and let's look at doing this one analytically, and just kind of take a look at how you're going to do this one then. Okay, well, one of the things that you got to kind of do with this one a little bit is you got to kind of apply a similar trick. You're trying to look at seeing if you can go through and work with that limit. The limit that we know is we know the limit as x goes to 0 of sine x over x. Okay, we know that that's equal to 1 on that. So what's going to happen on this one, we're going to eventually get to the point we're going to learn something called L'Hopital's rule, where just in seconds you can tell what the answer is. In fact, the answer is staring you right in the face. So what we want to kind of do with this one is think about if there's anything we could do to make those things the same. Now, you can't work inside the argument. All you can do is maybe divide by something. So here's what I'm going to have you do on this is we're going to do this basically. We're going to do the limit as x goes to 0, sine 3x, and we're going to divide that numerator by x. And then we're going to do the same thing here. We got sine of 5x, and then we can divide it by x also. You have to divide both the top and bottom by x. You have to. Okay? So what I'm going to have here is now I'm going to apply this little trick here. Guys, watch this carefully. Remember, I'm trying to look at sine x over x. So I'm going to multiply this by 3 over 3, kind of like I did on the last problem. And then the bottom, I'm going to multiply by 5 over 5. You're not changing the problem, because all you're doing is multiplying by 1, right? Okay? So what you would end up having is we're going to do a substitution. We're going to do 2 substitutions. So let's let u be 3x. Okay, so where we see that 3x, we're going to call that u. So those things are going to get changed to u like that. Okay, so you want to substitute these 2 things that I highlighted and just change those to u. So what you would have is the limit, x goes to 0. Now you would have 3 sine u over u like that. Okay, does everybody follow that? Okay, now let's do another substitution. Let's do v is equal to 5x. Okay, so everywhere I see a 5x, you're going to replace those things with v. So what you're going to have then is you'll still have the 5. So you'll have 5 sine of v all over v like that. Okay? Now, you got to know about limit theorems. The limit theorems we are real important for theory. What you're really doing is we learned that a limit of a quotient is the quotient of the limits. So we would write this as limit x goes to 0 of 3 sine u over u, all over another limit, x goes to 0 of 5 sine v over v, like that. Okay? Now we're getting close. Okay? What we're going to do next is you can bring that out of the limit. Okay, like that. So what we'd have is 3 times the limit as x goes to 0 of sine u over u. Then we'd have 5 times the limit as x goes to 0 of sine v over v, like that. Okay? So this is something I want you to see how the limit theorems go. Okay? Now, look at what goes on here. Tell me what this limit right there is. No, that one that I just highlighted. 1. It's not, it's going to be 3 times 1, right? Okay. What's this one right here? 1. Okay. That's what we proved, as we know that limit's 1. So what you'd have is 3 times 1, 5 times 1, so it's 3/5. Now students say, wow, all that work to get 3/5, I knew the answer anyway. Well, eventually you're going to see the pattern on this when we learn L'Hopital's rule. That 3/5 is the answer. But that's the analysis you have to go through to show that then. Okay? All right. So the key thing is that substitution. So let's go ahead and just put this in the calculator and let's verify this real quick and see if we got the idea. Okay. So if I put this in, I'm going to have sine 3x. Like that. You got to close parentheses, and then we're going to divide by sine of 5x. What? And let's see visually if it looks like what we expected. It's see if that limit's going to be equal to 5/3 or not. Okay, we'll just use the same window I did on the last problem. That's okay. And kind of a weird graph. It's got a bunch of asymptotes and stuff in it. That's a neat looking graph. So what we're interested in is the limit as x goes to 0. Okay, well what you could do is this. Okay, like if you traced at something very close to 0, like 0.01, what you're going to end up getting is, that's like 0.6. So if you look kind of at that, I'm going to go to the previous page here. You don't need to sketch that graph. The point is to see this visually. So what's happening on this, when I look at this graph then, is that's approaching 0.6. But 5/3 is, what do we get, 3/5? That's what 3/5 is. So if you take 3 divided by 5, you're going to get that value. Okay, like that. All right? So that's what I want to show you. A lot of times students don't follow this algebra on this very well with that substitution. What do you guys think? Tell me if you followed what I did okay. The main kind of key idea on that is you're just basing it on the limit you know. You're trying to rearrange things algebraically so you can do that then. Okay.
Can we skip steps in this problem?
Yeah, you can get, the thing about it is I want you to clearly see, you got to show that 3/3 and that 5/5. You have to do that. Then you need to write down your substitutions. Now you could skip like this step because you know that you're going the limit, you can break the limit into a quotient, and you know you can bring things out. I'm okay if you show this and go all the way to there. Okay, and then that's fine. Okay? All right, that's a great stopping point because what we're going to learn next time is the derivatives of the sine and cosine and the rest of the trig functions. So we'll look at that next time. Okay?